Tonight we're going to talk about the Michaelis Menten kinetics, and just want you to know when you're looking at your textbook, has a lot more derivations and a lot more math than we're going to need. We're really looking at this from a conceptual point of view. So a couple of key terms. V is reaction rate or speed, and Vmax is the maximum reaction rate. We're also going to see the term of substrate concentration, which is molarity. And then there'll be another term called Km, which I'll get to in just a moment. Okay, I want to get to this graph here. And what I want you to see is that this is a plot of velocity of reaction, how fast the enzyme's going with its substrate, and versus substrate concentration. So initially, let's look right here. Initially, if we add more substrate, the enzyme speed increases. And so if you notice, at first it's a linear relationship. So as the concentration of substrate doubles, the velocity or rate doubles. Now, if you think back to what we were talking about, that is suggesting that this is first order. So this part's first order. Now, as we keep increasing the amount of concentration of substrate, the velocity begins to flatten out. And so what we're seeing there is as the concentration doubles, the rate stays the same. And that rate is also the velocity. Okay, so the velocity or rate stays the same, and that's indicative of a zero order relationship. Okay, so this is one of the more famous graphs in biochemistry, and what it's telling us is that at some point, the enzyme gets saturated. That we can keep adding more and more substrate, but that the enzyme will not be able to catalyze the reaction faster. And eventually it'll hit a V maximum. So Vmax is going to be that point at which the enzyme is going as fast as it can to catalyze the reaction. Now, there is a very important term in chemistry, biochemistry, that is here at this point. Half of Vmax, I'm going to read it going across, and if I go down, we're going to note the concentration of substrate. And so the Km is the concentration of substrate that is needed to reach half of Vmax. Okay, so I'm going to click on this. So here, this is saying what I said on the previous slide, but in words written out. The maximum velocity of a reaction is reached when the active sites are almost continuously filled. And so if you increase the substrate amount after this point, you're not going to increase the rate. Okay, so Vmax is the maximum reaction rate. I'm going to click again. Okay, now at 1/2 of Vmax, so if our Vmax is 1, at half of that, at 0.5, if we read across and go down, we're going to be at and recognizing the substrate concentration that it takes to reach half of Vmax, and that's Km. Now, here's the really important part for us. Km is going to then tell us what substrate concentration is required to really start or really have a significant catalysis taking place. And then what it also will tell us is the strength of the enzyme substrate complex. So the smaller the Km, what that means is that the enzyme doesn't need as much substrate to reach max speed. So the lower the Km, the less substrate. Oops, sorry. Oh, that wasn't good. Hold up. Okay, the lower the Km, okay, the less substrate is needed to reach half of Emax. And what that means is that that's a pretty good enzyme substrate affinity. So it means that the enzyme has a high affinity for the substrate. Okay, if Km is bigger, that means that you need more substrate. And so the enzyme has a lower affinity for the substrate. So this can be, Km can be a good measure in comparing an enzyme's affinity for its substrate. Okay, and that this is it written out and not a better way or better writing. So if you notice here, it gives us an idea of the strength of the enzyme substrate interaction. Okay, so the lower the Km, sorry. The lower the Km, the higher the affinity an enzyme has for its substrate. Okay, so there's other ways to talk about the efficiency of an enzyme, and that is through kcat. And what that means is that that's the number of moles of substrate that react to form product per mole of enzyme per time. So this is assuming that the enzyme is fully saturated and that it's going at the fastest rate that it can, its maximum rate. So kcat can be used also to compare enzymes. And so if here's a chart of different kcats. So the catalase is really churning out a lot of product per second compared to some of these other enzymes. And so the turnover number can vary tremendously between different enzymes. We're going to be looking later at chymotrypsin. So that's an enzyme that we're going to be seeing coming up in the next presentation. Okay, our last section is going to be enzyme inhibition. This is a very important topic because we don't always want enzymes to be going at full speed. There's going to be times in glycolysis, Krebs cycle, metabolism that we want to slow an enzyme down. We don't want it to make product. And then there's going to be times where we want it to make product. And so the important idea here is that enzyme inhibition, there's going to be enzyme inhibition that's reversible, right? You want to slow it down, slow or speed up. Well, I guess we'd say we're going to just slow it down. And then when inhibition's not there, it's going to speed back up. Okay, so, all right. So there's going to be two classes of enzyme inhibitors. One is a reversible inhibitor. That means it's not covalently bonded or bound. And then there's an irreversible inhibitor that's covalently bound. And right now, this is an important discussion because there are many drugs that are developed that are irreversible inhibitors because you want to completely destroy that enzyme's ability. You want to slow it. In other words, you want it to bind and that's it. You don't want it to come back. Whereas reversible is more what we would see in metabolism enzymes. That you want as a point of regulation. Or way of regulation. Okay, so we're going to be focusing in class on reversible inhibitors. But on worksheet 2, which is not posted yet, we're going to be looking at HIV drugs. And that's the idea of this irreversible inhibitor. And I think the HIV drugs are a very interesting topic and one that's very relevant right now with what's happening in our world with the coronavirus. So we'll be doing that worksheet in a week or two. Okay, there's 3 types of reversible inhibitors. These are inhibitors that can bind, and then they can also disassociate from the enzyme. So it's almost like an equilibrium. And after it disassociates from the enzyme can recover its function. Okay. And what does it mean by non-covalent? It's not forming any bonds. It's more through attractive forces or intermolecular forces. So we're going to be looking at competitive, non-competitive, and uncompetitive. And then the irreversible inhibition, this one here, you're going to be looking at in your worksheet. Okay, so competitive inhibitors. So here's our enzyme and substrate. They complement each other, correct? By polarity, you have a polar substrate, the enzyme and the active site's polar. In a competitive inhibitor, you're going to have a competing molecule that's going to also resemble the enzyme active site as well. And so you're going to have a lot of similarities between the substrate and the competitive inhibitor. What will happen is that in the competitive inhibitor, to get the same speed of your enzyme, you're going to have to crank up and you're going to have to increase Km. I do not know why I keep doing that. I was not having problems with that before, so I think it's just how I'm resting my hand. So you have to increase the concentration of substrate, okay, if you want to essentially flush out the competitive inhibitor. And so what's going to happen if you have to increase the amount of substrate to keep Vmax the same, then what's going to happen is that you're going to see that Vmax is the same. Oh my goodness. One more time. So we're going to increase the amount of substrate, okay, to flush out the competitive inhibitor to keep Vmax, right, to keep it churning out at the same speed. And what's that going to mean is if you have to increase the amount of substrate to keep Vmax, then you're going to be increasing Km. So Vmax stays the same. The enzyme's going to go at the same speed, if you can increase the substrate amount. So if you have a lot of substrate around, then you can flush out the competitive inhibitor. This is showing it more in our equation format. See the E plus S, but now E is going to go and bind the inhibitor instead. Okay, but if you increase the amount of substrate, you're going to push it towards this way. Okay. Okay, non-competitive inhibitor is different. What that means is that the non-competitive is going to bind at a different site. You see how this is on a different site of the enzyme. Okay, and so it does not prevent the binding of the substrate to the enzyme. What this will mean, if I come over to the next slide, let's take a look at this picture because I think it looks pretty good. Here's your enzyme. It has a site right here for the substrate, and then on a different site, it has a site for the inhibitor. Okay, and so what will happen is that you have a competition, not a competition, excuse me. You have the inhibitor binds, and now notice what happened. It changed shape, right? So you can't bind the substrate. Okay, in other words, you're taking out the enzyme. It's not going to be there anymore in the same shape for the substrate. Now, what will happen is that you will have some of it, some of the enzyme will still be free to bind the substrate. So if it has a portion that's still free to bind the substrate, it's going to go and make product. Okay, it's going to go and make product. So what's going to happen here is that the inhibitor lowers the amount of functional enzyme. So the inhibitor lowers the amount of functional enzyme. Okay, but the enzyme that's around, so the enzyme that is available, can still bind the substrate, and so Km is the same. So Km's the same, but since you have less functional enzyme, then what will happen is that Vmax, how fast it can go, is lowered.